How about now? Can you hear me? Okay, great. Yeah, good evening or good morning, everyone. And my apologies for the delay. I had a bit of confusion about the time, but I'm very happy that I could manage to join you. I don't know, Julian, how we proceed. Should I go directly to the topic, or is there any initial? No problem. Yeah, thanks a lot for the kind introduction, Julian. Actually, I thought because I realized that already students have been familiar with Message and they have had online tutorials. So I focus mostly today on the theoretical part, and I will talk about I will show shortly what the topic of my presentation will be today. If there was another chance for doing hands-on, working with the model, some sort of again another session, then it will make sense then to go through the storage as a for presentation of storage in the model. But today I would probably mostly focus on economic and market economic aspects of energy storage. I realize that you have already discussed technical aspects, different technologies, so I don't take too much time on that. So maybe if I start to share my screen and can you see my screen now? Okay. Okay, great. Yeah. Okay. As mentioned, the topic today will be a general topic about renewable energy and energy storage systems. What's their connection and how energy storage systems can help us to integrate renewable energy. Again, my apologies for being a little bit late, and because of that, I jump to the topic. Maybe before that, I talk a little bit about my institution, about the IASA, which stands for International Institute for Applied Systems Analysis. This institution is a research institution in Austria, in Europe, and it has been since 1972, and with the goal, with the mission to bring science for policy making, using science as an interface for policy making. And it has different member countries. If you look at this map, those countries that are highlighted in dark blue, they are member countries of IASA. As you can see, Brazil is also a member country, and Professor Hunt has been also a member of IASA. And we have different schemes for collaboration, and I would like to invite you to keep this in mind as an option. If you are a PhD student, you can come to IASA for 3 months to do a research in the summer. We have a summer program. And of course, the past 2 years, because of the COVID situation, it has been virtual, but hopefully later it goes back to normal as you can have this type of short-term visit. You can come also for a postdoctoral study and work with different researchers. And altogether, IASA has almost 380 researchers from different countries working on topics that are mostly related to systems analysis. So we don't have any laboratory, we don't have any technology, physical work with the technology. What we do is we only have computers and we do modeling, systems analysis, and that is what the name stands for, International Institute for Applied Systems Analysis. And the areas are quite broad. So anything that you can imagine, maybe anything is a bit exaggeration, but many different systems that looking at those systems, studying those systems is not possible by only one discipline or by only one track of research. They require multidisciplinary research. These are what IASA is, good at that. For example, you think about energy, think about the ecosystem, think about water, and the different topics that you can see on this page. It is not usually possible that only one discipline can answer the questions in these, multidisciplinary and interlinked topics. So that's why researchers come from different disciplines at IASA to answer these questions. So if your master's studies or later your PhD is related to any of these topics, you can consider the potential collaboration with IASA. With that being said, I will move on to what I plan to talk today. I have the first part. I will quickly go through renewable energy systems again as an opening to the second part, which is related to energy storage systems. I realize that this course is mostly about energy storage, so I assume that you have had in-depth and different courses related to renewable energy. So my idea is not here to introduce different aspects of renewable energy, but I just want to make an intro to the energy storage part. Is there any question so far, or I can continue? I don't see any participants raise hand or whatever is actually. I see my screen. So Julian, please remind me if there was any question or if I should. Great. Great. Okay. So let's talk about a little bit about renewable energy and why there is so much emphasis these days, nowadays, about renewable energy. And then we go and talk about different systems and how integration of renewable energy in the power system specifically can be possible with the technology that we have today. I guess probably you have had in your courses or you have seen in the media, the challenge, the scale of the challenge is quite immense. If we look at this figure, which shows the primary energy consumption globally, and if you look at the horizontal axis, it shows from the middle of the 19th centuries when the industrialization started until almost today, we see that the amount of energy that human is using is enormous. And if you think, for example, initially we had only wood, then we started to use coal, steam power plants were invented, and electricity generation helped to move the wheels of the industry. And then we started with transportation, using a lot of oil, which continues still today, and using different sources of electricity like gas, natural gas for electricity, for heating, for cooking, and then nuclear. So human has been, a thirsty, eating energy, and the wheels of the industry has been, circulating, rotating by a lot of energy. And that's why we should think about how this trend can be reversed or can be replaced by a sustainable way of using energy resources, because we know that these resources are depletable and limited. But the challenge also is not only about limited resources. In the beginning of the 20th century, human being had this discussion that when will be the peak time for oil extraction, for oil production. This conversation about peak oil, peak time was very dominant in the 20th century. But as we improved the technologies and we started to produce, different conventional fossil fuels like shale gas, shale oil, we realized that the challenge is not about resources. Of course, resources are limited. They are not available for every nation, for every country, but especially towards the end of the 20th century and the beginning of the 21st century, the challenge of greenhouse gases and global warming became more evident. So if you look at, for example, at this figure, it shows how much greenhouse gases each type of electricity generation have. And as you can imagine, fossil fuels, either related to direct use of the fuel or related to the process of generation of that, conversion of that fuel and generation of electricity, they emit a lot of greenhouse gases, which are listed down there. And of course, renewable energy technologies like solar PV, hydro, biomass, they have also low amount of carbon emissions related to manufacturing material or other processes. But if you compare them, you see that the amount is not comparable. And what happens, as all of us know, the greenhouse gas effect, that these gases from different processes, from electricity generation, from mobility, from agriculture, they go to the atmosphere. And like we can see in the left side, a greenhouse for farming, for agriculture, exactly the same phenomenon happens, that they make these gases go to the atmosphere, they make some sort of shield, and they don't let the line wavelength radiation goes back, and they capture it around the globe, and it starts to make our planet warmer. Of course, this effect is needed. Without greenhouse gas effect, the temperature on the surface of Earth would be minus 15, minus 12. I guess it's a bit too cold for us. So we need the effect, but the problem is that as much as we are increasing the emission of greenhouse gases, the temperature is rising, and it's more than what is needed. So if you look at this figure, this is the global carbon cycle. Carbon cycle means different sources of emitting carbon and different sinks that they can absorb carbon from the atmosphere. So you can see that, for example, there is ocean that can have a carbon exchange with the atmosphere. There are forests. There are different processes. And if you look at the very left side, you see that these are carbon emissions that are being emitted due to burning fossil fuels. And that is the place that human starts to interfere with the natural, balance. So other processes, you see a lot of carbon is uh, being emitted from oceans, but more or less the same amount of carbon is being absorbed by oceans. Or if you look at other parts of the natural ecosystem. But the part that is human being is, changing this natural balance, that this natural cycle is when we extract fossil fuels from, thousands meters underground, we bring them on the surface and we burn them, and that is irreversible. It can't go back. So that is the problem. And if you look at this figure, it shows that almost 7.7 gigatons of carbon is greenhouse gases is being emitted to the atmosphere due to human activities, and that has caused the global surface temperature increase. So again, if we look at after industrial revolution, in the left figure, we look at the average global temperature, we see that it has been increasing quite significantly. And to the right, you see that if this trend continues, we will be on that red track, and the warming at the end of the 21st century will be something maybe 4 degrees. And that is why all the scientists or different environmental organizations are concerned that we should, stop this trend, and we should try to keep the warming below 2 degrees or well below 2 degrees. So I guess with that very, I would say, general intro to the problem, I want to pose this question to you. I mean, look at this figure. It's showing the impact or the effects of climate change. And you see there are some numbers and there are some cartoons, animations. So I would like us maybe, I don't know how much time we have. Yeah, maybe we spend 4 minutes on this figure. So please look at the figure, and maybe each of the students pick 3 of these items and write down in your, paper or in your notebook that what these impacts are, and are there, for example, something related to the society, economy, health, and then we discuss a little bit after that. Okay, so I take the time now. I would like everyone to look at this figure and pick 3 items, 4 items, depending, and write down in your paper that what that impact is and how this impact is affecting the society or economy. Okay. Exactly. No, we will discuss. We will discuss. Yeah. I'm sorry. I don't see the yeah, I don't see the panel or the list of participants. Maybe I yeah, I see that now 3 minutes is passed. So I can open the discussion, the floor, if anyone would like to mention any of these numbers or discuss them, please chime in, raise your hand, or some of them are mostly related to the environmental impacts, physical impacts, and some of them to the right side is more about societal and economic impacts.
Yes, thank you, Julian. Yes, so for me, that I'm already working with this in my PhD, so it's a little bit obvious that I looked for the number seven, and which is wind patterns change that can um, cause more damage to increase more hurricanes and a lot of other climate change impacts. And in the number five, we have the precipitation uncertainty and also more storms and, you know, and then I can pick the number 10. That's with a warmer climate, we can have more melting ice, more melting glaciers, and this can affect the environment, the animals that living over there. Yes, I think that's it.
Great. Yeah. Thanks a lot, Natalia. As mentioned, yeah, number is 7 and 5 are related to extreme uh, weather events like storms or hurricanes. And number 10, as you mentioned, is melting and sea level rise that can cause, for example, as we can see in number 17, migration. And migration itself then has some other consequences that we can see, for example, in number 11. It can be, people going from one city to another city, people going from one country to another country, which might causes social unrest or unemployment or other problems. Any other thoughts?
Hello. I picked just two numbers. The number 13, it's related to the crop season to grow, the famine. Uh, but it's like a controversial because it also uh, includes the monoculture. So it's also an economical and also a climate change related topic. I also picked the number 10, the defrosting, uh, and the rise of levels of the oceans and something like in this way.
Thanks, Paolo. Yeah, some countries are already facing drought because of higher temperatures. And that drought might, as you mentioned, reduce the harvest of different food products that might also cause other consequences. Okay, if there is no other thoughts, I guess I can show you in the next slide. Oh, sorry, my apologies. I don't see the. Yes, please. I can hear you. Can you hear me now? Okay, great. No, I can. Number 16. It looks like Corona. I don't yeah, I guess it's related to the spread of because of change of the temperature, spread of viruses, and I guess I can move on to the next slide, which shows us usually when we have the possibility to have different groups, I usually ask this question. Some of these might sound a little bit simple or trivial, but usually it also brings this discussion that how this, affect the society and economy. I mean, we are a little bit more familiar with the environmental and, physical impact, but consequences for the society to the right side and for the economy is also very important. So as mentioned by some of the students, there are some direct effects like higher temperatures and like different impacts on different parts of the ecosystem, and there are some indirect effects like, as we discussed, migration and social unrest and failure in providing enough food and enough resources for everyone. So I guess we have probably discussed in your other courses, or you have heard already in the media about different impacts of the climate change, direct or indirect impacts. But here the question comes that to what extent the planet can handle, can accommodate these changes. So one of the institutions, for example, as you can see in this headline news in 2018, they talked about the hothouse state, which is a state that imagine that planet has been in balance for millions of years, and it has reacted to different stimuli, and different cause and effects have been counterbalance each other, and the planet has been in balance. But now we have a human that is interfering with the planet, with the climate, with the pace, with the speed that is considered to be more than the speed that the nature can react, the nature can, sustain. And that is the problem, that when things become unsustainable, when we, use something and without replacing that sustainably, that causes the problem. And if several of these ecosystems, imagine about the forest, about ocean, about, different natural ecosystems, if they get out of balance, if they go out of their natural balance, there might be a domino effect. And these researchers actually argue that if this domino effect happens, then human is not able to, make that stop or to reverse it to some extent. So all of these scientists are warning us that we need to do something before we reach to a point that things become out of control. It might sound a little bit like a futuristic movie or some sort of, but these are scientific work. And of course, one can argue about different methods, different way of doing that, but it's good to understand, or to at least read and see what different opinions are talking about. So what we can do, I mean, now we talked a lot about the problem, but is there any solution to that problem? Yes, there are some solutions. And of course, some of these solutions have been discussed a lot for, different contexts, different countries, depending on their resources, their potentials. And here I have listed just a few of them. And with the focus on the energy sector, because again, it depends on the country. In some countries, 70%, 80% of the greenhouse gases come from the energy sector. in other countries that are mostly based on agriculture, there will be less share from energy, more share of greenhouse gases from agriculture. But here, there are a few solutions that can help us to cope with the problem. Like, for example, reducing energy consumption, material energy efficiency, and changing lifestyle, changing behaviors. For example, I guess all of us now during the COVID, we realized that, of course, all of us are tired, all of us are stressed, all of us are under pressure. But at the same time, we learned that some of the processes could be done online. I mean, I'm not advertising that. I know that everyone wants to say now, no, that's enough. We want to go out. But nowadays, in many countries in the world, governments have started to use more actively these online platforms. For example, if you want to do a tax work or if you want to do some other things and you don't have to go to that office. So these type of solutions, depending again on the context, they can help us to cope with the problem. And from all these solutions, I picked renewable energy because this is the topic that we want to discuss today, and we look at that a little bit further in details. But it doesn't mean that there is no other way of doing that. And usually there is not only one solution. We need to capture whatever we can from different solutions. And here we just talk about renewable energy. Renewable energy today, if you look at this big square in the middle, or more or less to the left, it shows that from the fuel that we consume today, only about 20% is renewables. I'm talking about fuel for the whole energy system: electricity, transportation, and heating, cooling, and cooking. And again, from that 20% renewable, only 10% is modern renewables. Modern renewables like wind and solar, and modern use of biomass, and traditional use of biomass is also another part of that, which is 9%. Traditional use of biomass is like collecting wood in developing countries from the forest, from the neighboring areas, and burning that, which is not a modern use of renewable energy, and it has also its own consequences. And again, if we go further down to the right, we see that only 1.4% of the energy consumption worldwide is coming from wind and solar and modern biomass and geothermal, which is wind and solar, which is quite little if you compare, for example, with the fossil fuels that still they constitute a big part of our energy use. On the other hand, if we look at the resources, you can imagine that the resources, the potential for renewable energy is much, much higher than fossil fuel. So if you I don't talk about the numbers here, but if you look at only the yellow circle, you see that this is the solar intake, solar irradiation that reaches the planet. And if you compare that with what resources or fossil fuel resources we have, coal, oil, and natural gas, you see that it's much more than whatever resources, fossil fuel resources we have. And this is for every year. I just would like to pick two technologies that have been groundbreaking. One is solar PV, probably from different countries. If you come, you have realized that, or you have seen that there has been a lot of improvement in the uptake of this technology, mostly because the cost has declined dramatically in the past 10 years. So if you look at this figure from 2009 to 2019, you see that it's a picture for the global statistics. from 23 gigawatts, we reached to 627. And that is quite very, very impressive number. And there are also different countries, as you can see. China is the forerunner, and there are other countries like the States, Japan, Germany, and India. And as you can imagine, the technology is modular, the technology is easily installable in different places, is economically competitive in many countries already, is accessible, and it's maintenance free. It doesn't need any water, it doesn't need any regular maintenance. And if you look at the capacity additions, meaning that the new installation every year, and this number is for 2009, these numbers are for 2019, there has been 40% growth globally in 1 year compared to 2018. So there has been a lot of new installation of solar PV, and in some countries it can be as cheap as 1.4 cent of dollar per kilowatt hour. So it's a choice for developing countries, because initially people were complaining that these technologies are expensive and we need coal, we need fossil fuel to burn. But now if you look at the economy, you see that these technologies are not expensive anymore. So if you look at the figure that I have put here, you see that in 2019, if you look at the orange part, which is about the capacity that was added in 2019, you see that some forerunner countries like Vietnam, Ukraine, these are developing countries. So when the technology is becoming economically competitive, so even developing countries can afford that, and it's a very good news, and it can come to the grid parity, which means that the electricity generation from solar PV is economically competitive with other sources. And of course, if you look at the left part, again, China is the forerunner. The capacity in China alone is more or less, the added capacity in China alone is equal to the rest of the world, which is a good news because we know that China is one of the main producers of greenhouse gases, and this is a good news. Again, the same pattern, more or less, for wind, a lot of installation in the past 10 years. I don't go through the details here, but again, the technology is, quite modular. It can be distributed. It can be in a larger scale and wind farms, and it's again available everywhere in many countries. And I know that in Brazil there is a lot of discussion about the potential of wind in answering some of the problems. Again, here India is the third country in capacity additions in 2019. So this brings me to this figure, which is, if you remember the figure that I showed you about the amount of energy that we use, you saw that 80% was from fossil fuel. But if you look at the investments in 2019, it's about the new power capacity investments globally on new power plants. You can see that 70%, more than 70% has been renewables. And this doesn't include the large-scale hydropower. So it's quite an impressive number. It's a bit, I see that there is hope when I look at this figure. And of course, as an expert, as an energy consultant or engineer, if all of us look at this figure, we should figure out that where the money goes. So 70% investment in renewable energy, and the rest of that going to nuclear and fossil fuel. And that is actually a problem. When we are talking about renewable energy compared to fossil fuels, fossil fuel industry has been traditionally concentrated, in the hand of a few, as opposed to renewable energy that creates, more jobs and more technicians, more experts will be involved. And of course, in some countries that they have a very well established fossil fuel supply chain, that is a problem that becomes a resistance to do the transition from fossil fuel to renewable energy. But again, when we look at these numbers and we see that the costs are getting lower and lower, it brings this hope that the trend would be reversed, and at some point, like it happened in several countries, especially in Europe, traditional utility companies that are mainly focused on fossil fuels, when they saw the advantage of investment in renewable energy, they also started to at least to invest in renewable energy besides their other assets. If we look at the share of renewable energy in the power sector, we see that Denmark is one of the forerunner countries, pioneer countries. 60% of electricity in Denmark comes mainly from wind and solar. And then we see other countries like Uruguay, Ireland, Germany, and others that they have 30% around, about 30% from wind and solar. So this is the situation. I just wanted to talk about mega trends, global trends, that's what's happening. And if we think about the cost of electricity, probably you have heard the concept of levelized cost of electricity, which means the amount of investment that we do on the technology divided by the amount of electricity that technology generates over its lifetime. So cost over lifetime divided by electricity generation over lifetime. And this is the figure that compares renewables with other sources. So for example, if you look at the blue part, the light blue color, it shows renewable energy sources. And the dark blue part shows the fossil fuels and also nuclear. And of course, there is a uncertainty range depending on the different costs, insurances, installation, and tax. And in different countries, it's a bit different. And these figures are without subsidies. So it's just comparing the cost of the technology. And as we discussed, and as you can see, for example, here, solar PV and wind are becoming economically competitive, almost the cheapest. And even solar PV rooftop for the houses is still a bit on the more expensive side, but in some fossil fuels and nuclear is also economically competitive. Okay, now I would like to, maybe we will have a 5 minutes break or maybe 7 minutes. Yeah, and think about this question while you're grabbing your cup of coffee or water, or you're having a break. When we are back in 6 minutes, we talk about a little bit what is the challenge, because we talked about renewables and we showed that the cost is going down. So what is the challenge? Why, for example, in some cities, countries, or in some electricity grids, there is still a challenge to integrate renewable energy. Okay, so if there is no question, have a short break and let's come back in 6 minutes. If you hear me, let us continue. Can you hear me, Julia? Okay, great. So the question was that what are the using renewable energy in the electricity sector specifically? So I would like to open the floor if there is anyone wants to share their thoughts. I see Marcos' hands is up. Please, Marcos. Is that hand for Marcos or for Paolo? You are muted.
We are not hearing you, Julian. Oh, yes, I can. Okay, so for me, it's providing power on demand, even when it's not sunny or windy. And also the market volatility, because the renewable energy are uncertainty and the market is also uncertainty, so that can be a little bit more tricky. And also the transmission infrastructure to satisfy customers' peak demand. I think for me it's the most challenging effect.
Yeah, thanks, Natalia. So you mentioned three challenges. One was variability in renewable energy sources, that they are not there at the time that we might need them. The second was is that correct, or
Yes, yes.
Okay, great. The second one was related to uncertainty. For example, if usually power systems plan, for example, for the coming days or hours to deliver electricity, and if you don't know how much wind or solar will be there, it's a bit difficult to plan, and especially if it goes to longer terms. For example, next year, how the weather will be and how much availability there will be. And there was also some of these technologies are far from the electricity grid. So how to bring them to the, for example, windy areas might be far from the grid, and it might be challenging to bring the electricity to the grid. Any other thoughts?
Yes, I would say despite the cost, we still have intermittence and weather dependence. I think this is a more challenging part to deal with.
That's true. Laura, do you have any solution in your mind if one can cope with the intermittency?
Well, first we have the option to storage energy. I think that's the solution we can have.
Thanks, Laura. Any other thoughts? Okay, I guess I can start to share my screen again, and if there was anyone who wanted to add something, please. Is a new hand or old hand?
No, it's an old hand, sorry.
No problem. Okay, let me try again. Okay, let's wait a few seconds. Do you see my screen?
Yes.
Okay, great, thanks. So yeah, as discussed, these challenges are broadly put under the umbrella of intermittency challenge, which means, like, for example, solar and wind, they are variable. They are sometimes there, they are weather dependent, there might be not there in a few hours, and it makes them temporally and location location-wise variable. There might be some areas in the country or in a city, they might have sun, other areas might not have. Or in some countries, for example, wind farms are near the coasts, or in other places that need electricity consumption, places like the cities, they are far from the wind farms, and it makes the challenge to how to either extend the electricity grid or make some sort of balance. And of course, because, for example, in hot climate countries, you need enough electricity in hot seasons or in warm seasons for cooling, for providing air conditioning and cooling. And you don't know that, of course, if you are using solar PV, you might have some, estimation that how much of that solar PV is there. But if you are, generating electricity from wind, it might not be very easy to say that how much wind will be there for generating electricity when there is a peak demand. Also in cold climate countries like that, in cold climate countries, the peak demand is in winter, and so solar PV doesn't really contribute to meeting the peak demand. So whatever you put wind and solar PV, you still need other, power plant capacity to be there. Sometimes they are just only there standby, just only, imagine you have several cars. Some of them are just parked there to be used a few hours per year. So of course, for power system planning, it's not an ideal situation that you invest in some assets that are not being used very often, and they are just there for be used a few hours per year. And we talked about grid connection issues that either you want to bring from far areas to the city, and in some places that people put a lot of solar PV on the roof. And when it's a lot of sun and people don't have electricity demand, that electricity from buildings, from houses, goes to the grid. And again, it causes a grid contingency or grid traffic. And that is also another challenge that in the distribution grid, there should be some measures to cope with this flow of electricity coming from buildings. So these are some of the things, or some of the integration costs of these technologies. So as mentioned by Lara, the cost of technology itself is going down, but still there are some additional, measures or costs that should be taken into account. And here there are a few of them that we discussed, like with the students that mentioned, and a couple of things that we added here. Also, last not but the least, these technologies, solar and wind, because they are highly variable, they change from one hour to another, the rest of the system should be quite flexible to respond. Imagine that if you are a team and you are delivering a task, if one person is absent in some hours, coming back next hour, the other people has to work out how to manage this type of variability. So these are the challenges that power systems are now coping with, the integration of solar PV and wind. And here is a snapshot. Of course, it's quite old. It's from 2011, but still you can imagine that 10 years ago it was a challenge. Still, it's a challenge. And the challenge is that if you look at the electricity demand up there, and you see wind in the blue area, and here is in January in Europe, you don't have that much solar PV. But you see that in some parts, like for example, of course, 1st of January is an exceptional case. It's a holiday and not so much industry is working, but wind is so much, close to the electricity demand. And in some hours later in the month, there is no wind. And of course, you need to have other capacity to fill the gap between these two. As discussed, there are some solutions for the intermittency challenge. For example, one solution is demand response. to adjust the electricity demand to, to match the demand and supply together. There are other solutions like converting electricity to other forms of energy. For example, in some cold climate countries like Denmark, when there is a lot of electricity from wind, they convert that to heat, like using electric boilers or heat pumps. The electricity is converted to heat, and then thermal storage is, of course, much more economically competitive and profitable. So then they use that heat, of course, for providing heating services for the buildings and other solutions. But here we talk about electricity storage. Again, as I mentioned, it is one of the solutions. It's not the only solution. And there are a wide range of solutions for coping with the intermittency challenge. And what is electricity storage? As you know, in this course, we are talking about storing electricity to be used later at a reasonable response time. So we are not talking about, for example, making fuel storage or using electricity, for example, for demand response or this type of reactions. These are, of course, other categories, but we are specifically today talking about technologies that store electricity in a different form of energy, and then they convert it back to electricity when we need it. Okay, so and again, as you know, I don't really spend too much time here because you have learned in this course that usually, in general, most of the electricity storage systems can be divided in two distinctive parts. One is power conversion system, and another part is storage part. If you think about pumped hydro, it's easier to think about that you have turbine and pump, which is the electric machine or the conversion system, and then you have a dam, you have a reservoir that you put water there. So, and as you can imagine, if you look at the start from, for example, from input energy, you have your losses during the charging, you have losses during the storage, keeping the stored media, and you have also losses during the discharge, and that is make the overall efficiency of a storage technology. There has been a lot of research increasing demand for research, R&D, research and development on energy storage. One of the reasons we talked was variable renewable energy, but storage is not only for variable renewable energy. There are other reasons that nowadays it's a topical issue, it's a hot topic. One is this deregulated electricity markets. Private electricity markets or deregulated electricity markets. There is a lot of variations in electricity price. So some people think it might be useful to use storage to, fill the gap between electricity prices. Also, there is a high investment needs for extension of the grid. And later we see that electricity storage can help us to reduce this cost. And of course, like we discussed, the cost of technology is declining. The cost of batteries is predicted to decline. And that makes another motivation that we start to use these technologies more actively. Because you know that batteries have been in use since the 19th centuries. Actually, the first electricity grid that Thomas Edison invented, it already had a battery, because even then they knew that the electricity demand and supply might not match, and they used the lead acid battery for balancing the grid. It was even before the 20th century. But of course, nowadays, the situation is becoming different because of different reasons that we have mentioned here. I'm assuming you have learned about the technologies. I don't talk about the technologies in detail, so you can now lay back and just look at a few slides that I go quickly that shows how different technologies work. And if you look at this figure, as you know, technologies have different ranges of specification, different efficiencies, different power capacity rate, from very small technologies, small power output, to large pumped hydro power plants, and the delivery of or the discharge time can be from seconds or milliseconds to days and months. So we are talking about quite a wide range of technologies, so that's good to keep that in mind. And it can be, as you see, mechanical or electrochemical or chemical. Pumped hydro is one of the technologies that I guess is quite well known. It's commercial. It has been in use in many countries since 20th centuries. It can be as large as 3,000 megawatt. So it's like two big or one big large nuclear power plant. So it can be large, and it can provide long discharge time, and it's a technology that doesn't need any fuel, or it doesn't have any emissions. The drawbacks is that, of course, these are very large and sometimes complex projects. It really depends on the geology and geography. It's not possible to do that in every place. It's very site-specific. And in many countries nowadays, environmental permitting is very difficult to make these reservoirs in the ecosystem. And of course, they are very capital intensive. They need a lot of upfront investment costs. There are new variations of that. For example, this is one example that in some areas that you don't have enough elevation between the two reservoirs, you can make an underground reservoir. And here is, for example, like a empty piston that you fill it, with water, and then you can use electricity to lift the piston. And when you need the electricity, you release the piston, and it presses water, and it generates electricity. So these are different types of pumped hydro. Again, there is also this type of seawater pumped hydro that one of the reservoirs is using sea at the sea level. And of course, there should be some refining of the water, but yeah, that is also one possibility. Another technology, compressed air energy storage. It's not fully fuel-free. Of course, there are advanced compressed air energy storage that doesn't need fuel, which uses the heat from compressor. But in general, the concept is like a balloon. When you have excess electricity, you compress that to a cavern or to a tank in a high pressure. And when you need that electricity, you release the air. Imagine you release the balloon and it goes and it gets the momentum. That air goes out and it rotates a turbine and it generates electricity. Again, it's a large-scale technology. It's proven. All the parts are commercial. Compressors, motors, generators have been there for many years. The problem is that the fuel efficiency and it's quite low efficient power, low efficient storage, between 42 to 50% efficiency, and there is heat recycling with recuperator. And also it's because it needs fuel in most cases, it's it has uncertainties related to the fuel cost and emission cost. Another technology, flywheel. Again, if you look at this, I don't know the name in English, this thing that we used to play when we were kids. The concept is more or less similar to that. So you give a rotational energy imagine there are two chambers here, one inside another, and there is a very little friction between them. So when you rotate the first one, at some point a clutch make them engaged, and then they rotate together. It's a good technology. It's already in use in some of the trains for the braking system, and it's again a commercial technology. It has been used for bridging when you have, for example, a power system in a very sensitive area, for example, I don't know, a data center or an application that you really need electricity to be 100% reliable. This technology is very useful because in milliseconds, it can bridge if you have, for example, a blackout, electricity is cut, this technology comes in a millisecond, and it helps to bridge the power to the reserve capacity or reserve power plant. They are modular, and they can be used also without, of course, fuel, and there is no speed or, yeah. Sure. Mhm. That's a good point. Maybe the main reason that they use them for braking, as you mentioned, is that first of all, this is a mechanical technology, so it needs a shaft to rotate it. So there is no chemical involved. So in the first place, if there is any mechanical rotation, if there is for example, imagine an electricity generator or any other mechanical device that has a rotating power, it can rotate this device, the chamber. And when the rotator either is an electricity generator or it's a train, mechanical force, when it is stopped, then this device continues to still rotate for a few seconds, maybe 20 seconds, 30 seconds, depending on the mass. And that rotation is enough to generate electricity. So for the trains, for example, if a train comes and stops to the train station or metro station, this device is continuing to rotate. For example, imagine 30 seconds, 1 minute when the passengers go up and down. And then when the train wants to accelerate again, start to work, that rotation helps the engine of the train or the device, so that it doesn't use a lot of, again, momentum to start from static point. Exactly. So they use that movement. It's some sort of storing momentum, storing rotational energy. Welcome. And that's why it's very suitable for frequency regulation in power systems, which is exactly the same application, keeping the momentum. And as you can imagine, it's not suitable for energy-related services. You don't want to put electricity here and come back in 3 hours, because then there is nothing left. It's stops after a few minutes. And of course, batteries, that I guess in this course there has been a lot of discussion related to them. Again, they are modular. They can be increased in higher capacities, 30, 40 megawatts, 50 megawatts. And of course, they have some downsides, like material intensity or toxicity, or for some of them, you need air conditioning to keep them cool. I don't go through the details, but again, one of the ways to store electricity is to convert electricity to gases. It can be either in terms of hydrogen energy storage, you use electrolyzers and you convert electricity to hydrogen, and that hydrogen can be used, for example, in fuel cells, in even it can be mixed to some extent up to 5% with the natural gas in the gas grid. It can be used directly in hydrogen fueled vehicles. And that is also one way of storing electricity. But of course, we are more interested in the electricity to electricity. So that would be mostly fuel cells here. Again, it's a very good solution for long-term storage. Technology is available, and it can be converted to different energy carriers, not only for electricity. It can be used for heating. It can be used for transportation, which is very important. And I guess, as you can imagine, this is one of the technologies that still is on the agenda, and there is a lot of research because you can convert renewable energy, renewable electricity to different energy carriers. And of course, hydrogen has a very high energy density, but the problem is low efficiency and high capital cost. If you further continue this hydrogenation, converting electricity to hydrogen through another process, reacting hydrogen with CO2, we end up with synthetic methane or synthetic natural gas. So this process is called methanation. So again, imagine that you have a lot of electricity, you don't need them, for example, in the grid because of what we discussed, intermittency challenge. You convert that to hydrogen, then you can also absorb CO2 and react them and make natural gas. And this natural gas has the properties of, this synthetic gas has the properties of natural gas, so it can be used again for transport, heating, and for electricity generation. And the good news is that it can be stored or it can be transmitted through the existing natural gas grid, which will be very interesting. Again, the problem is that the efficiency is very low, and it's 32 to 40%. And again, the cost of this, the whole processes is quite high. But you can imagine that the energy density, the amount of energy that you can store in a small tank or space is quite a lot. And if you were interested, you can think more about power to gas. There are several companies or startups developing different ideas, like, for example, this company that is thinking about a sailing boat that goes to the seas. It's an unmanned boat. It doesn't need any onboard person. It doesn't need any sailor. So it goes to the ocean, imagine, without any destination. It just goes and looks after the wind, where the windy areas are. And usually, of course, in the ocean, the wind is more stable and there is a lot of continuous wind. It generates electricity, and it also converts that electricity to fuel and goes back to the harbor. If it is feasible economically, I don't know. If you are interested, please go to that webpage and read more. But of course, there are some other companies that use wind, like, for example, this big tanker that is using this sailing device, which has been one of the use cases of wind that human being has been done for ages. So still, it shows that we can use that for even in modern devices. And they argue that it increases fuel efficiency, if I remember correctly, by 20%, which is, of course, considerable. Yeah. Mhm. Mhm. Yes, I have heard. I guess I don't have a good figure to compare, but I guess here the argument for this ship, if I assume you are talking about the left one, this ship. The argument here is that, as you said, it has this cylindrical wind mills, you can say. The argument here is that compared to offshore wind, you don't need to install, you don't need this installation, cost of wind, because this technology is already used in some boats. I have seen the figures that this cylindrical wind turbines that shows here, wind goes in and, it circulates and it makes a, force to drive the boat. It's already, they assume that this is less costly compared to making, offshore wind. But I see your point. If the offshore wind becomes cheaper than this, then that might be more attractive. Another argument here was that the boat can go to the ocean, quite far from the harbor. Exactly. It has its own storage and it doesn't need any electricity grid. So it can go and, go anywhere that there is a wind and capture that and make it, convert it to fuel. Welcome. Okay. So I guess we are more or less familiar with some of the functionalities of electricity storage. Sorry. If you look at this figure, this shows a typical electricity demand in 24 hours. So horizontal axis is 24 hours. Yeah, during the night, we have low electricity demand. Then we start the day with different devices. Electricity demand goes high and it reaches its peak at some point. Again, depending on the country and climate, these peaks can be a little bit in different hours. But again, everyone comes back home. You use home devices and lights, and at the end, electricity demand goes low when we start to go to bed. And of course, for meeting this electricity, as you can imagine, even without renewables, this was the plan or the way that electricity systems were run, that you had some baseload generation, usually those plants that we want to generate the whole day, the whole even weeks and months, which are nuclear power plant, for example, coal power plants. And then we have some load following power plants that they can adjust their generation for a few hours. And then we have those peaking plants that only come, for example, at the peak time. This was even without renewables and without storage. And you can imagine that if in this power system you bring storage, first of all, you can fill the hole here. There was some hours that you couldn't make an economic baseload generation. This is one of the services that storage can provide, which is usually called capacity firming. And actually, this was one of the first services that in the US they used for pumped hydro to what they call it, firm the capacity of nuclear generation. So imagine that you have a nuclear power with this much capacity. You want to make sure that it runs all the time because it's very cheap, and you don't want to also reduce the generation. It has a lot of maintenance costs. So they use pumped hydro. And of course, on the other hand, when you discharge electricity at the peak time, so you charge it here at night in this blue part, and you discharge it at this time. And here you reduce the need for additional capacity. So you don't need peak power plants, which are usually very high pollutant or high carbon emitting gas power plants. So this is one of the first ideas that they use storage, even without renewable energy, to make a little bit a balanced shape of the power supply and demand. So this was one of the services or benefits. Now we want to talk quickly about some applications and benefits. I know that we are a bit running out of time, so I go a little bit quickly here. Usually in this part, I pose this question to the students that, and also now I want you to think about that, but we don't have time to discuss in the group, that what are the use cases and benefits of storage? So we talked a little bit about, intermittency challenge, about capacity firming, about reducing peak generation. Are there any other services that comes to your mind? And who benefits from that service? Because we saw that storage technologies are in different sizes, in different technologies, and there might be different owners for that. You might have a battery at home, you might have a pumped hydro plant that is for the energy company or the government or the utility company. And there might be other technologies for other stakeholders in the system. So it's good to keep in mind that, first of all, what benefits storage can provide and who benefits from that service. Is it consumer, is it power generator, or is it system operator? System operator is the entity that is responsible to bring electricity through the grid to the consumers. It's not necessarily generator. In some countries, these two are the same, generator and system operator. If we look at this schematic of a power system, it's a very traditional power system. If we look at, for example, here is a central power plant. So this was the way that our cities and our power systems, are working. Our power systems are providing electricity for our cities. There are central power plants. Then there are, high voltage transmission grid. Then it comes to, for example, low voltage distribution transformators. And then at this low voltage distribution grid, we have, for example, for different communities, different industries, residential, commercial sector, and different factories, electricity is being, distributed. And as you can see, this all these circles that are highlighted in red, they show different locations in the power supply chain that energy storage can play a role. So you can imagine that it's not only about end users, it's not only about renewable energy, there are different services. So if you look at this figure, usually, as I told you, if there is time, we talk about the different applications. I listen to the students and we count until 18 applications. But here I just quickly name a few of that and then we go to the next. So a group of services that energy storage systems can provide are called ancillary services. Ancillary services are those services that help the grid to maintain frequency and to maintain, for example, the required voltage. So, for example, if you imagine, we talked about the flywheel, imagine that in a power system, if the frequency goes low, imagine if you have a bulb or lamp, the light starts to become a little bit with less intensity. It becomes a little bit dimmy. You can see that, you become worried that what's happening. So that is when the frequency goes low. But if you have a storage that can help the grid to increase the frequency, then the light goes back to the normal, and you say, oh, okay, no problem happened. So this is a very simplified explanation of that, but there are different services even in these ancillary services, like reserves, like balancing, like different, which is mostly in the area of power system engineers. Then it comes to bulk storage. Imagine, for example, here we were talking about wind power plants in the coastal areas, okay? So if you have a wind power plant in the coastal areas, for example, imagine you have a very big wind farm with 100 turbines or 200 turbines. Sometimes it's not possible to build the electricity grid with the maximum capacity of the wind, because it doesn't make sense, because not all the time these wind turbines are rotating. So it might be useful to have some sort of storage nearby if you don't want to build a large transmission line. You can manage the wind generation already near the coast and make a kind of stable and with the lower capacity coming to the grid. And then it comes to distribution grid. You can have, for example, here you can use storage for peak shaving. Imagine you are in a neighborhood when there is electricity demand in hot summer days. Sometimes you see that, for example, the grid doesn't work and there is a blackout or there is a problem, or what we are seeing nowadays in Texas, that electricity grid has collapsed. So if there are this type of contingencies or this type of traffics, you can manage that with storage, and you can reduce the load on the grid. You can, reduce the pressure on the grid. And of course, storage can be used at the end use. Imagine you have a factory or you're at home, you have a battery, and you use that battery for example, shifting electricity from night to day, or do some other, price arbitrage, or using battery for increasing the reliability. If your industry is very sensitive and you can't afford not having electricity, you might use it for reliability services. So there are, as you can see, a very different range of services that energy storage can provide. And in this type of figures, usually they show that these services that we were talking, for example, who benefits from that? Is it end user? Is it the grid operator? Or is it a utility company? Or is it the independent system operator? And of course, again, they have different ranges, for example, from seconds to hours, and also different capacities. So this is, I guess, a good schematic that shows us what benefits we can get from energy storage systems. Of course, these benefits really depend on the market design. Market design, I mean the electricity market. In some countries, for example, electricity system is a monopoly of the state. So the generation and distribution, transmission, all of them are in the hands of, the state. So in other countries that they have a liberalized or deregulated power market, these services are controlled by different entities. And that is also a challenge, because in some areas, for example, in most of the countries, transmission and distribution, this part is run by the government or by the state. And that is why usually it's for energy storage very difficult to get into this part, even though this is a part that is very profit-making for the storage. Okay, I guess I escaped this one. This is about price arbitrage. We discussed about that you can charge the battery at night or electricity storage at night and discharge it during the day. Of course, it depends on the prices. I will share the slides later with you, so I don't go through these details, but this is also what we called about ancillary services that, for different ranges of time energy storage can provide different services for the grid. I talk a little bit about this slide and then I guess we can finish. One of the challenges is that if you look at this figure in the left, here we are talking about economics of electricity storage systems. And by economics, I mean costs and benefits. Imagine that you want to invest on electricity storage, either for your home or for your industry or for the electricity grid that you are working for. Of course, you will think about cost and benefits of any investment that you make. Here, if you look at the cost, usually the cost has a fixed component, which is related to capital cost, and a variable component, which is related to the operation of that asset. And of course, you want to have the benefits that will be higher than the cost because you don't want to be, you don't want to have a loss. And here is some scale of different benefits of electricity storage. Usually it is argued that the highest benefit from electricity storage is when you use it to avoid building new electricity grid or to avoid upgrading electricity grid, as we discussed, for example, either near a wind farm or in the city, because electricity grid is very expensive, expansion of electricity grid or upgrading the electricity grid. So this service from energy storage can make a lot of money or can save a lot of money. Then, of course, you can use storage for providing system capacity. We discussed, for example, at the peak time, when, for example, there is no solar and wind, you can use storage to provide capacity. You can use storage for energy shifting from night to day, usually, again, depending on the country, depending on the price volatility from night to day. This service is not very lucrative in terms of economic because, for example, in many countries, the price gap between night and day is not enough for electricity storage to become profitable. And there are, of course, ancillary services like reserve and regulation. So if you think about the very left part, which is the cost, and think about the benefits, usually so far with the cost of the electricity storage today, in most of the markets, none of the services can alone make enough benefits to break even the costs or to be, net positive return. Of course, again, there might be exceptions, there might be some cases, but this is a very common understanding. What is argued usually is that if you could use storage for providing multiple services, if you could provide, for example, several of these services at this, together, which is a phenomenon called the revenue stacking or aggregation of benefits, then if you put these benefits together, it might be higher than the costs. But of course, this is a theoretical, potential. Technically, storage cannot do a lot of things at the same time, so you have some limitations. So you come to the technical potential. And of course, not all of these services are being paid, so they are not monetizable. So if you want to make money, again, you will come to some, lower stack, lower sum of the benefits. So there is also another problem with the storage that it has a self-competing effect. So imagine that if you put storage, if your neighbor puts storage, if anyone puts storage, then the benefits that all of you can get will become also less and less because the price gap, becomes lower. Those urgency of the need of storage also becomes less. But here there is an argument that usually storage providers argue that, okay, so far we were talking about economic benefits, but also storage can provide societal and environmental benefits. If you remember when we were talking here about these services here, if you put a storage here, you're helping the society to integrate more wind. If you put a storage here, of course, you are helping to, for example, reduce the emissions from some gas power plant. And it's not only about the economy, but also about reducing emissions and increasing renewable energy in the system. So that is why some storage providers argue that if we internalize this, what is called externality. Externality is a benefit that a technology provides, but the owner is not paid for that benefit. They argue that if we internalize these externalities, then there might be a business case or a better business case for energy storage. So this is a very hot topic. If you are doing a research and if you are optimizing, for example, storage, or you are modeling storage, usually this is one of the topics that researchers are really interested, how they can use the storage asset for providing multiple services, for providing, for example, energy and water storage at the same time, or this type of thing. I guess with that being said, I guess you are also tired and I don't want to talk too much. My apologies again for losing a few minutes in the beginning, but I conclude by just mentioning some of the challenges and limitations. So the idea here today was to talk about a bit about applications, benefits, and economics of energy storage systems, specifically electricity storage systems. First of all, we should acknowledge that there is a lack of information about the economics of storage, because not all of the technologies are at the commercial level, or they are not adopted widely in different power systems. The second challenge, which is known, is that there are not free markets for some of the services that storage can provide. As we discussed, storage can help the electricity grid. If you even put a battery at your home or in your industry, you are helping the electricity grid because you are reducing the contingency and the peak, electricity exchange. But it's very difficult to prove that, or to technically measure that and to ask the electricity grid to pay you, and they would never do that. In many countries, it's not possible. And also, regulation, policy support is very difficult for storage, because again, it's very difficult to define the cost benefit, to make a cost benefit analysis. Why I say it's difficult? Because, for example, imagine you have a storage at home. If the government wants to pay a feed-in tariff, for example, for solar PV, they can measure that how much solar PV can generate, how much a solar PV panel can generate per year, and they make an estimation and they give you a subsidy. But for storage, sometimes it's difficult that if this electricity is coming from, for example, solar PV to this battery, or is it coming from the grid? So it needs a little bit of more smart metering and more complex metering compared to just the traditional ways of metering. And that also is related to, for example, if you think about in some countries, when you use electricity storage, when you are charging electricity, you have to pay tax, because they see electricity storage as a consumer, like a battery or like any technology that consumes electricity. And when you discharge electricity to the grid, they also tax you because they consider storage as generator. So this is a lack of regulation, that storage is not categorized separately. So it is double taxed both as consumer and as generator, which is also an inefficiency in the regulation. And of course, we talked about self-competition. Again, effect of high penetration of storage in the system should be taken into account. And we talked about aggregation of benefits or revenue stacking. Also, it should be kept in mind that electricity storage is not necessarily a green technology. Some of these technologies are really material intensive and they have environmental impacts, and that should be also taken into account. So all in all, storage is not a single solution. It needs to be compared with other alternatives. And that is why we need modeling, we need systems analysis to compare the advantages and disadvantages of different technologies. We need more commercialization of these technologies to evaluate cost and benefits and to make the economic aspects more clear, to encourage investors to make investment in storage and make business models. And yeah, societal and environmental impacts of the storage should be taken into account. And I guess with that, I have talked about what I wanted to share with you. I will be very happy if there is any questions or any comments that you want to make. Otherwise, I stop here sharing. I will share the slides with you, and I have a couple of links to different articles or book chapters that can be useful for you.
Thank you so much, Bernard, for your amazing lecture. It was very interesting. You addressed a lot of topics. It was interesting also because I have given an introduction to energy storage, but that was 2020, beginning of the end of September, I think. So this works very well as a summary for the energy storage lecture, which is always good to recap topics. Yeah, any question, guys? Additional question?
Yes, I was wondering after Bernard's talks about the life cycle analysis of storage. I think it's a really important research object to do because of the differences and costs and the primary energy costs. Just I don't know if
Yeah.
it's a question or it's just an affirmation.
Yeah, that is true. I guess probably for any other energy technology, storage also not excluded. Life cycle analysis provides a better understanding of the whole, technology and environment and societal cost. And specifically for storage, because it's in its early stages of adaptation, still there are a lot of policy and regulatory barriers. So as we discussed, some of them we mentioned here. So these are also interesting things to keep in mind, that if this technology is useful, do we need to change some of the regulations to make it easier for the owner of this technology to provide the service, to get benefit for that service? How we can measure, how we can monetize the benefits that the technology is providing? These are also some challenges, either if you want to do a cost benefit analysis or life cycle analysis. These are important to understand the streams of benefits and streams of costs of the technology.
Yes, perfect. Thank you.
Any other questions? Renan, in your opinion, the biggest current challenge for energy storage is political, regulatory, technological, or engineering? Or are they in the same impacts? Or do they have similar impacts?
Yeah, I guess it's a very difficult question to answer. In my opinion, it's more about regulatory and political, I would say, policy, energy policy situation in different countries. Of course, technology is still expensive. It's not a very cheap technology, but we see that in some countries that they provide some incentives for storage, or simply, for example, I can share with you a study that shows that we don't have to pay subsidy, because always when you talk about regulatory support or policy support, people say that, okay, we should pay subsidy to the owner of storage. No, we don't need to necessarily. The regulator doesn't need to give huge subsidies to storage owners, but to give them access to the services that they can make money. For example, one of the requirements in some countries was that if you want to provide ancillary services, the services for making balancing and reserves, you must have, for example, minimum 20 megawatt capacity. So it makes many batteries or many small scale, storage systems out of the competition. But now we learn that there is possibility to do aggregation or virtual power plants to bring several and provide that service. But still in many countries, it's not possible to do aggregation. It's not possible that you give access to the battery that you have at home to a central controller, which might be a small company somewhere that controls 1,000 batteries at homes and provides that service to the grid, and they get a lot of revenues. So these type of things that are, I guess, very interesting to look at that. But of course, technology is still developing. And yeah, if you are looking after research questions, I would say one of also interesting things, how we can capture the synergies between electric vehicles, because electric vehicles, if they will be vehicle to grid, if they have this option to give back electricity to the grid, they can be storage systems. So that is also another thing that might be in the future a solution, that you use the battery both for mobility and also providing services for the electricity grid.
Thank you so much, Ben. Any more questions?
Yeah, thanks a lot. And I'm very sorry for taking your time too much. And I know that it's very difficult during the lockdown and listening to this lecture for a too long time. And I'm very curious to know you more. I hope there will be another opportunity to listen to you, what you do, what's your master's or PhD degree about. Today we didn't have the chance to have an introduction from your side, but yeah, let's hope that there will be another opportunity to know you more.
Thanks, Bernard. Renan said that your lecture was amazing. Natasha,
Okay.
thank you, Bernard. Clara said thank you for your lecture. It was amazing. So congratulations, Bernard. Thanks so much for your time.
Thank you so much. I'm very happy to hear that. Thank you so much. Okay, have a nice day, everyone.
Bye
And
bye.
hope to see you
See you.
sometime.
Bye. Thank you very
Bye.
much.
Bye.
Bye. Thank you.